We have the score for each candidate parent set, and we try to assign each variable a parent set so that the corresponding network is cyclic and it has a total, minimum total cost. There are some additional constraints that we won't mention here, which benefit from symmetry and dominance relations to efficiently solve the problem. And CP-Bayes also uses a pattern database to compute lower bounds. When it works pretty well, but sometimes Gobnelk computes much better lower bounds. Now, before we compare these two solvers, let us think a little bit about how we solve BNSL or any other difficult problem in general. Usually we have so many solution alternatives that we need to examine. We need to somehow reduce the number of these alternatives to a reasonable amount, and we do this by taking decisions and by estimating the consequences of our decisions. So we need to perform inference to have a better view of the current state of the problem in order to reduce the solution alternatives we need to examine. So how much time we dedicate to deciding what to do next is actually a very important question to answer, because we may spend little time on thinking at each step and make more moves per time unit. But on the other hand, if we actually take more time to think, we might maybe able to see much earlier that a particular path will not lead to any better solution. So are we wasting more time by exploring more solution alternatives that we actually don't need, at least some of them, or by thinking more? We can visualize this question with this axis of inference, where at one end we have the speed and the other we have the strength. Note that although this seems to be a continuous line, it is actually discrete, meaning that we jump from one point to another with every algorithm or heuristic that we implement, and ideally we jump towards the middle. So Gobnelk and CP-Bayes lie at the two extremes of this axis. So Gobnelk efficiently takes into account the current state of the problem, given the decisions it has taken so far during the search of the optimal solution, and performs a very good estimation of the consequences of any decision that one can take as a next step. This is why we say Gobnelk performs a very strong inference. On the other hand, CP-Bayes is not necessarily as good at taking effective decisions, but it discovers a much greater number of solution alternatives per second, which eventually makes it competitive to Gobnelk. So our main purpose is to achieve a good trade-off between these two extremes in order to improve the state-of-the-art for BNSL. So we implemented a solver that we call ELSA, and it is based on CP-Bayes, the source code, I mean. And in this solver, we have a stronger inference algorithm for the global acyclicity constraint, an algorithm that discovers not all, but a class of cluster cuts that provably improve the linear relaxation, a greedy algorithm for solving the linear relaxation using these cuts, and finally a preliminary binary decision tree implementation for the domains of the parent set variables. So most of our algorithms use the Acyclicity checker developed by Van Beek and Hoffman for their CP-Bayes solver. And this Acyclicity checker does not carry out any domain value removals, but it simply looks at simply looks at the current domains of the parent set variables in order to check if one can construct at least one complete solution that is acyclic. And for that, they try to construct a complete ordering of the variables. And this is an ordering where a variable comes before another variable, if and only if it can possibly be one of its parents. So they start with the empty set in which they try to add variables one by one. So here I can start with variable 1 because it can have the empty set as its parent. The same for variable 2. And then I can add 0 because it can have 2 as its parent, which has already been added in the set. And it continues like this. And if we manage to add all the variables in the set, it means that the acyclicity can be satisfied. The time complexity of this algorithm is O n squared d, where n is the number of variables, which is 5 for this example, and d is the biggest, like the largest domain size, which is 3 for this example, although in practice d is like much larger than 3, but also than n in general. So we developed an algorithm that achieves generalized arc consistency, GAC, for the global acyclicity constraint. So let us talk a little bit about what we mean by GAC exactly. So it means removing all candidate parent sets from the domains of the parent set variables, which cannot appear in any acyclic solution. In other words, which definitely lead to some cycles. So achieving GAC is one very strong inference one can perform. But how to achieve GAC, or whether to achieve GAC, in other words, like removing some values leading to cycles instead of all of them, it is another important question to answer, and it is closely related to the speed of inference. Ramik and Hoffman observed that it is possible to achieve GAC by running the acyclicity checker for each candidate parent set of each variable, assuming at each time that it is the only candidate parent set that this variable has in its domain. So this means n variables times d values times the complexity of the acyclicity checker, which gives us O n cubed d square operations in the worst case, which is catastrophic because d is, as I already said, very large. We can have data sets where we have around 100 variables with 10,000 candidate parent sets for each. And indeed, Ramik and Hoffman also showed that the cost of doing this is too high to be beneficial. And we found a way to perform GAC in a cheaper way. We know that a BN can be encoded as a permutation of the variables, such that a variable always comes after all of its parents. So if we look at this BN here, 2 has no parents, so it can come first. Then we remove 2, and see that 0 has no parents. And we continue like this, and we obtain the ordering of this BN, which is 2, 0, 3, 4, 1. So in our GAC algorithm, we focus on each variable one by one. Let's assume we first focus on variable 0. And it is currently at the second position. At this position, 0 can have either the empty set or 2 as its parent, and nothing else, no one else. So we run the acyclicity checker with the condition that 0 is placed no earlier than the third position to see if other variables can also come before it, so maybe they could also be one of its parents. Given that we have n variables, therefore n positions, we can push 0 down at most n times, and we have not only 0 but 4 other variables for which we do the same thing. So it gives us all n times the complexity of the acyclicity checker, which makes all n to the power of 4 times d operations in the worst case. And although the power of n increases from 3 to 4, it is still a gain because we got rid of the d square, and yeah, d is usually much larger than n. So we later realized that it is actually not necessary to rerun the acyclicity checker every time we want to push down a variable in the ordering. So let's assume again we want to push 0 down in the ordering. And it is enough to find another variable w in the suffix, the set of variables succeeding 0 in the ordering, the purple variables here, 3, 4, 1, a w in this set, which has a candidate parent set that is a subset of the prefix, the set of variables preceding 0, the orange ones. Once we find this variable, we can actually insert it, the W, we can insert it just before 0, provably without ruining anything. This is a faster way of pushing a variable down in the ordering in order to maximize the set of variables which can potentially be a parent of 0. Once the variable 0 reaches its latest possible position in the ordering, we remove all of its candidate parent sets, which are not a subset of the final prefix. Now, we have n variables, n positions, and we do n times b value checks when we look for a new w in the suffix. And this gives us a total of all n cubed d operations. And we empirically showed that this very favorable complexity does result in significant performance improvements. Now, we ran experiments with 69 data sets, of which I will share the ones with the most interesting results. So in this table, we look at the results of 4 medium-sized data sets with less than 64 variables and 3 large data sets with more than 64 variables. The third column is the sum of the number of candidate parent sets of all variables, which can even be cubic in the number of variables for some data sets. We compare our solver ELSA, which uses only the GAC algorithm for now and nothing else, to CP/S in terms of the CPU time taken to find the optimal solution and to prove optimality, as well as the number of search tree nodes. So the data set above the line here had a time limit of 1 hour, and the ones below, they had a time limit of 10 hours. And we see that the number of nodes is systematically smaller for ELSA, and the CPU time is either the same or slightly better for the medium data sets, and much better, nearly halved for the large data sets. Now we will see how we can multiply the gains from GAC with a better lower bound mechanism. So we developed an algorithm in order to generate a lower bound, which is computationally cheaper than that of GoldMilk. We identify in polynomial time a subset of cluster inequalities, and not all of them like GoldMilk does, which provably increase the lower bound. And we also implemented a greedy algorithm for solving the linear relaxation, which takes into account these cluster inequalities. We detect violated cluster cuts by running the acyclicity checker in a way that it considers only the values with 0 cost. So I will try to give an intuition using an example instead of just talking about technical details. So here it would be a good idea to actually see these costs here as marginal costs, meaning that whenever we assign a variable this value, it would increase the lower bound by, for example, 6. So we see that the graph constructed using only 0 cost values contain quite a few cycles. And indeed, if we were to run a acyclicity checker using 0 cost values, already in the beginning, there would be no variable that we could add in the ordering, like in the set, because there is actually no variable with the empty set in its domain with a 0 cost. So when this is the case, it actually means that there is no acyclic solution whose total cost is equal to the current lower bound. Therefore, we can increase the lower bound. So we call it a cluster when we have a set of variables where a cycle is inevitable, and the acyclicity checker fails to add any variable in the ordering and therefore returns the entire set of variables 0, 1, 2, 3, 4 as a cluster. So in order to get rid of the cycles, we need additional constraints that we call cluster cuts. We do this on a special type of clusters called violated clusters to make sure that the lower bound will increase. And we observe that in a cluster, there is no variable whose parent sets, whose parents are all outside the cluster. Therefore, we must force at least one variable to take a set of parents which are all outside the cluster. So here, a variable 1 or 2 or 3 could have the empty set as their parents, whose intersection with the cluster is the empty set. Therefore, this would solve our problem. And for variables 0 and 4, however, there's no such parent set value. So yeah, we focus on these 1, 2, and 3 here. And as a result, we have this new constraint. So either V1 or, either V1 or V2 or V3 equals the empty set. Once we have this new constraint, it is clear that we'll have to pay a cost of at least 5. So we can actually deduct this cost of 5 from the cost of these 3 values and add it to the lower bound. So as a result, 6 will become 1, 10 will become 5, and 5 will become 0, and the lower bound will increase by 5. We can try to increase the lower bound even more. So instead of taking the violated cluster returned by the acyclicity checker as it is, we can first try to see if we can minimize it. So again, I won't go into details, but know that it is possible to minimize the set 0, 1, 2, 3, 4 to the set 1 and 2. And if you actually look here, you'll see that between variables 1 and 2, there is actually a cycle, so it makes sense. The cluster cut then becomes V1 equals the empty set or V2 equals the empty set. And this way, we get to increase the lower bound by 6 instead of 5, which was the case earlier. So in this table, we compare GOBMILP, CP by S, ELSA using only GAC, and ELSA using GAC and these cluster cuts that I just presented in terms of the CPU times taken to find the optimal solution and to prove optimality. The solvers again had a time limit of 1 hour for the datasets above the line and 10 hours for the datasets below the line, and the crosses indicate a timeout. So as a cluster is the winner in terms of the number of datasets solved to optimality, and in terms of the CPU times, as a cluster is the overall winner half of the time, and still much faster than CP by S and ELSA got most of the time, making it even more competitive to GOBMILP as opposed to CP by S. So let me just take a sip for my tea. So before, both algorithms I have presented so far, they have a factor of D in their worst case complexity, which made us think that we could further improve the performance of our solver with a more compact representation of the variable domains. So within these two algorithms, we repeatedly ask these questions. So, does there exist a parent set value that is a subset of a given set S? Or does there exist a parent set value that is a subset of S with an associated cost of 0? Or does there exist a parent set value that is a superset of a given set S? So answering these questions require looking at the values in the domain of a variable, and in the worst case, we might actually end up looking at the entire set of values. And given that D is huge, it is clear that there is a big potential for improvement at this point. So we use binary decision trees to represent the domains of the variables. The binary decision tree is a data structure which can be used for classification, and each node corresponds to a criterion with respect to which we classify a set of elements. And each branch leaving the node indicates if the elements fulfill this criterion or not. A dashed branch means it does not fulfill, and a solid branch means it does fulfill. And here we use a decision tree to classify, for example, 4 objects into 4 different classes, and using 2 different criteria. The numbers on the branches indicate how many elements flow from one node to another. So we can actually use binary decision trees to represent domains, like we do here for a variable V0. It has 4 candidate parent sets, V1 or V2 or V3 or V1 and V2 at the same time. So the root node takes all of these candidate parent sets as input, and it classifies them with respect to the criterion of containing V1 or not. The following nodes do the same for other variables until we have exactly one candidate parent set at each leaf node at the end. So this way we actually have a unique path from the root to the leaf for each candidate parent set. And note that the order of the variables on which we branch can actually be determined by any heuristic that we may wish to use. Different heuristics result in different tree sizes, actually, and we use the tree size as a proxy for how fast we can answer queries. And in our work, we use information gain to determine the variable ordering, which is a well-known heuristic used for this purpose. So we implemented this binary decision tree representation for the domains with ELSA, and in this table we compare GOBNILP, CP-Bayes, ELSA cluster, and ELSA using like DAG cluster cuts and binary decision trees together with information gain heuristic. So ELSA IG is the winner in terms of the number of data sets solved to optimality, even though it fails to solve one data set that ELSA cluster was able to solve within the time limit. And yeah, I think that's pretty much it. So in this thesis, we made contributions to the state-of-the-art in learning the structure of PNs, mainly Bayesian Network Structure Learning problem, which is an NP-hard problem. And all our contributions helped us achieve a better trade-off between the inference speed and strength of inference. So in particular, we came up with a strong inference algorithm with a very favorable worst-case complexity, a lightweight lower bound mechanism inspired by the ILP method developed for BNSL by GOBNILP, and a decision tree implementation which made the propagation faster, especially for some data sets. Now, as feature work, one possible direction could be to consider using a dedicated LP solver for the LP relaxation we use in our BNSL lower bound algorithm. For example, the existing nearly linear time algorithms for solving positive LPs. And we might also consider computing parent set scores during the search, which would indeed increase the solving times, but it could potentially decrease the overall time needed to generate the scores for a particular data sets and solving it to optimality. So that was all. These are the links to the solvers, to the data sets used, and our publications based on this work throughout my doctoral studies, and the references used in the presentation. So yeah, thanks for your attention, and I'll be glad to answer your questions if you have any.